was almost nil in this region. So that is the basically his trigger point. And since then, he didn't stop. He is now basically taking all the heights in all the possible direction. He has contributed when he was just completing his PhD in the PDF time. He contributed significantly for the first time again in the warp model, as some of you know. So there is module for the aerosol, and that was missing. So that also for the particularly black carbon that he introduced. Then again the for CO as a tracer, that was also he worked, and that is also during his PDF time. So these are the few achievement, and then since then he is now in NCAR. And when he joined the NCAR, that was also I will say he was the first Indian to join NCAR in the atmospheric science community. He has been achieving a lot of awards, and particularly now recently he got the award from the Belgium Academy of Science. Name I just missed that name. Baron Nicolette Award, yeah, and yeah, and he has almost 125 papers with him. And his maybe another interesting thing I just saw the last month, his citation index in Google is crossing 10,000. So that is at this age is very difficult to achieve. And of course, he is not guiding any PhD student and post from Indian region also. When even he was doing postdoc, that training session he started. So with this, and also, yeah, one more achievement I would like to point out. During his postdoc or when he was just beginning his career in NCAR, I think he in presentation he'll be covering that one program map AQ. So of course, officially he is the co-founder or co-chair, but co-founder or co-chair with none but other than the Guy Brasseur. So you can compare in the atmospheric science community what is the level of Guy Brasseur, and he was basically the sharing the activity and started this MAP AQ program. And this MAP AQ program you can see now very active in the globally in different region, and he has done wonderful work in the African region. Somehow we were also trying to see same thing in Asia. So, but it is taking maybe some different shape, and that is also recognized by the IGAC activity. So, with this, I request the Rajesh to speak and share his experience.
Okay, can you hear me? Okay. Okay, thank you so much, Manish, sir, for these kind words and nice introduction. I think it is always a special feeling to be back in Nainital. This is where my professional journey as a researcher started. I will be forever grateful to this place for giving me the platform, um, all the necessary um, infrastructure, instruments, and everything so that I could do my PhD here. Today, I'll be talking I'll be focusing on this topic of air quality predictions. What are the challenges? How can we be innovative? And what are the opportunities that are there? I think it is a very exciting time to be an atmospheric scientist, and I will try to demonstrate that in today's presentation. So let me start with this picture. So air pollution means, I think is there anyone who has not heard about the word air pollution? If we all have heard about the word air pollution, then let me tell you, the day mankind invented fire, we also discovered pollution, right? But the real research in the air pollution started because of these type of episodes. And this is a photo from 26 July 1943, when the first smog episode hit Los Angeles in the US. And when this episode took place in Los Angeles, it was a big shock for LA residents. LA was considered to be the land of pure air. People believed that if you have tuberculosis, it can be cured simply by moving to LA. That was the belief at the time. And so look at the year. Can anybody tell what was a major event happening during that time, a global event? World War II. So the first reaction of the LA residents was it's a chemical attack by Japanese. Nobody thought that it's an air pollution event. And so it took 8 years for Hagen Smith, who was a professor at UCLA, to tell the LA residents it is their own cars and their own industries that are leading to this air pollution episode. Then, as politicians do, this event occurred on 26 July. 27 July, the mayor of Alice, they temporarily shut down the Aliso Street plant, but smog persisted. In August, the mayor announced that we will eliminate this problem in 4 months. And the problem still exists today, more than 70 years later. I already said that. So I think since then, the community has invested a lot in fundamental air quality science. And so to solve any problem, we need this combination of integration of the measurements with the modeling capabilities to solve any problem. So here I'm highlighting some of the investment of the community over the last 70 years that has led to advances in our fundamental understanding of air pollution science. There are laboratory studies that are done to understand how chemical reacts in the atmosphere. Then we try to bring that knowledge into our models. We conduct field campaigns, and those field campaigns are also conducted at ARIES. So when I joined as a PhD student at ARIES, we would frequently put our ozone monitors on the mobile labs. We would drive from here to Pantnagar and come back. And I think I heard this morning that the students are doing that even today. So you don't need to have an aircraft to make vertical profile measurements. Like here at ARIES, people are demonstrating just by driving up and down the mountain, you can make vertical profiles of major vertical profiles of air pollutants. In situ measurements, like the ground-based stations, cannot be put everywhere. So the community has launched satellites to have better spatial coverage. Initially, we launched polar orbiting satellites that provide recording stop. Do we need to? I'm fine with either. Okay. Okay. So basically, you see that there are lab studies, field studies, the satellites have been launched, and observations are always the basis of our fundamental understanding. The knowledge that we gain from the observations, that is the knowledge that we then try to put into models so that we can better interpret observations. We can use these models for predicting what is going to happen in the future. But in addition to the advances in the atmospheric sciences, we also needed advances in the computational sciences. And the advances in computational sciences has allowed us to build very large supercomputers on which we can run these models. So this is the photo of our NCAR supercomputer called Derecho. And this is where we run most of our models. On the right, I show a lot of the infrastructure that ARIES has developed over the last 20 years. And it is remarkable to see that within 20 years, an institution that has nothing to do with atmospheric sciences has grown kind of a national scale infrastructure for monitoring of atmospheric composition. This science is very necessary. I started with that picture of LA. So if you go back to the temporal trends, this is not going back to 1943. It is going from 1960 to 2010. And if you look at hourly ozone levels in red there, the maximum ozone recorded in LA, this is surface ozone I'm talking about, it's 680 ppb. We still do not see that much ozone at any place on the planet. The maximum ozone that we recorded at ARIES during my PhD time was 120 parts per billion. So you can see what was the magnitude of air pollution problem in LA at that time. A lot of our megacities in India are going through the same problem. But these type of graphs, which shows us that we can reduce those pollutants. It gives us motivation, it gives us confidence that we can solve this problem. We just need to find the right approach. It was because of a lot of the cars didn't have any emission regulations. None of the industries had any regulations. So the emissions were very, very high. And LA's topography is such that it is like Delhi. Everything gets accumulated into that valley and it gets cooked up, and it leads to the formation, a lot of the formation of ozone. So this is the pointer? Okay. All right. And this is for advancing. Okay. No, this is blue line is the maximum 8-hour average ozone. So basically what you have is this one. Oh no, this is the national ambient air quality standard for the US. Yes. And so, yes. But even after so much reduction in LA, we have not been able to meet the national ambient air quality ozone standard. But it is not a problem specific to LA or Delhi or any particular city. It is actually a global threat. And the recent estimates show that nearly 8.4 million people die prematurely in the world because of exposure to air pollution. And nearly 2.18 million of those deaths, about 25%, are taking place in India. So it's a very serious problem for India. About $5 trillion are estimated to be lost because of the exposure to air pollution, with $36.8 million in India, which is, I think, closer to 31,000 crore rupees in Indian currency, and 80 to 120 million tons of crop production is lost because of the exposure to surface ozone. So we did a study back in 2016 together with IITM, where we estimated that if you save all the food that is lost because of exposure to ozone, we can feed 94 million people in India that are living below poverty line. So it's a huge threat to India, to people in the globe. But most of the expertise in this field lies in the developed world. Like the problem started in North America and Europe, and naturally scientists, they started studying this problem. Now it has become a huge problem in Asia. If you look at China and India, these are the two countries that are suffering the most. The trends have started declining in China, but in India, especially PM 2.5 continues to rise. So if we want to solve this problem, we cannot solve this in isolation. And that was really the motivation behind starting this international activity. We call it MAPAQ, Monitoring, Analysis, and Prediction of Air Quality. And the objective of this activity is to develop and implement a global air pollution monitoring, analysis, and prediction system for air quality with downscaling capability in the regions that are affected by high levels of air pollution. So we particularly focus on Asia, Latin America, and Africa. And as Manish sir said, I am the co-founder of this activity along with Guy Brashour. It is jointly supported by both the International Global Atmospheric Chemistry as well as the World Meteorological Organization. We proposed 5 components for this activity. The first one is, of course, monitoring, which is we have state-of-the-art monitoring facilities at ARES as well, because monitoring always provides us the first information. It is very important for evaluating the predictions. It helps in initializing our models better. The second is modeling, because with the models, we can predict things in the future. And that way we can inform the decision makers and tell them about if there are upcoming air pollution episodes, what type of actions they need to take. But you have measurements and you have models, and all of them provide information in scientific language, right? If I tell a person at the street that PM 2.5 today is 100 micrograms per meter cube, they won't care about it. It doesn't mean anything to them. So we need to convert that information into something that is easily understood by the public as well as the decision makers. So interpretation is the third component that is essential to this system. And then once you have translated it into some type of information that can be easily understood, then you have to disseminate it to the public. You have to get it to them via websites, via SMS, mobile alerts, those type of things. And then finally, training and education. We cannot expect any country to solve this problem unless we have local leaders in that field. So it is very, very important that we work together. The developed world needs to take a backseat role. They need to come in a support role, but we have to develop local champions, local leaders, local expertise within the country. So the capacity building, training, and education is very important. So far, we have a lot of activities going under this initiative. So we have activities in the US, South America, Europe, Africa, Middle East, India, and China. And so we are continuously trying to expand our reach and trying to bring researchers together. So why do we really need air pollution forecasts, right? I touched on this a little bit. We can protect public health through air quality warning and alerts. We can protect ecosystems if we have prior information about how much pollution is there. This is very important for short-term regulatory actions. Like I'm sure some of you have heard about GRAP, activation in Delhi, the Graded Response Action Plan, and the forecasts are used to inform their implementation. Medical infrastructure management, that is something that is not practiced yet, but that could be another potential application. So for example, if there is a pollution episode approaching, and we know that in a particular area, there are a lot of people with respiratory problems, they can use this information. The hospitals can expect more respiratory related admissions into polluted days, but this is not used for now, but it could be one application. If we are able to protect public through reduced exposure to air pollution, then of course we will be able to keep the population healthy. And if they are healthy, they will be working more. So we can increase public productivity, which will then translate into economic benefits. And then it is very important for public awareness and education, because government can make policies, they can try to enforce policies, but it is individual actions that matters the most in terms of mitigation. All right, so I am now going to focus on air pollution forecasting, and we do forecasting based on the models. I have said the word model quite a few times in my talk today, but what is a model? Does anybody know what is a model? I'm not talking about the one that do ramp walks, but just anybody. Whatever you can think of, you don't have to be shy. I know you are smart people. But anyway, if you don't feel comfortable, a model is nothing but it's a simplified representation of a complex system. That's all what it is. So a lot of people get scared by the term modeling, but when we say model, what we are trying to do is we are just trying to simplify a complex system in a way that makes it easier for us to understand. So the question then next is, what is an air quality model? So the definition still holds true, right? And we have all been building our own heuristic models, right? Means when we are kids, we do not know whether we should go on the road or not, right? But as we grow up, we gather a lot of information about what is the flow of traffic on that road, at what speed the traffic is coming. And we do our own mental predictions of like how much time I'm going to take to cross this road. And we trust that prediction and we cross the road, right? So we all have these type of models every day. So technically, all of us are modelers. So if you think you are an observational person, you are also a modeler naturally. But what goes into an air quality model? So we know that it is nearly impossible to have a measurement station at every point on the planet. So what we do is we try to kind of where is this pointer going? Okay. So we divide the globe into different grids, right? And so you can assume that this room is a grid box. It is a model grid box. This is how it looks like within a model. And so within this grid box, what is happening? So at the surface, you have a lot of emissions happening, right? If we are in a real world, assume that this room is 10 by 10 kilometer, right? 100 kilometers square. So there will be traffic, there will be agricultural activities, there will be residential cooking activities, there will be industrial activities. So I need to know how much emission flux is going into my grid box, right? Once it gets into the atmosphere, it has to be processed by the chemistry. So their winds are there, they will transport it around. Then we have solar light coming in that is going to dissociate these pollutants. The pollutants are going to react with each other. And that, so those are the things that the chemical and aerosol processes that you see, which also depend on the weather parameters. And then there are some processes that you cannot resolve, which means like, say, for example, if we have a little bit heat source at the floor and it leads to a motion that rises, but then it reaches the equilibrium at this level, which means it doesn't reach the roof. So in terms of the model grid scale, I only have information at the floor at and the roof. But because this process is starting at the floor, but it is not reaching the roof, I cannot resolve it in my model. So I need parameterizations to resolve that process. So that's why whenever you hear about any atmospheric model, you also hear a lot about parameterization. So there is no model that explicitly resolves all the physical and chemical processes. And because of that reason, all models are wrong. But as scientists, it is our job to make them useful. So we have to understand what are the limitations of a model, in what circumstances I can apply it, in what circumstances I cannot apply it. That is our job. Now, when we are talking about this, we are just thinking about this room, right? We are not disconnected from the world. So there can things, if the wind is blowing into this direction, then pollutants will flow through this wall, exit that wall, right? If the wind is blowing from that direction, same thing will happen in this direction. So you have to stack all these grid boxes together and cover the globe. That is your model, right? With the information that you have about the physics and chemistry of the atmosphere. So this is how we build the model. I'm not going into equations, but if anybody is interested, if you understand how the Navier-Stokes equations work, how you solve them, you basically have a very high probability that it will be very easy for you to understand how the model works. There can be multiple modeling applications, and I'm taking too much time, so I probably should skip over this. But predictions is really interpretation of observations, and predictions are really the important things that we need the models for. All right, Delhi air pollution. This is a hot topic, and I call it as an evolving story of science in service of society. Sorry, there is a mistake here. It is in. It should not be is. Okay, so people who have lived in Delhi or who have lived in India, they know that the main sources of emissions that affect Delhi are anthropogenic sources. People live where people live, they will lead to emissions. Farmers in Punjab are blamed a lot for problem in Delhi, right? So, and this is a source, it's a real source of problem. It is because that in Delhi, you are already up to here because of your own emissions. And then when farmers burn the crop stubble, it gets here. And when things go over your head, that's when you start shouting, right? We don't hold ourselves accountable until we are doing things just for our own. And then dust storms in spring. They also bring a lot of dust from the Middle East and Thar Desert into Delhi. So these are the major sources affecting air quality in Delhi. Plus then interstate transport is a major contributor. And so this is a work that I did with Piyush. Several of you may know him, but you can just focus on this plot here. And so here what I'm showing is the percentage contribution of each state to air pollution in Delhi. And so the top row here is for carbon monoxide, which lives in the atmosphere for about a month. And this one is for black carbon, which lives in the atmosphere for about a week. So now you can see that Haryana and Punjab and Uttar Pradesh, these are the states that contribute, say, more than 5% of pollution in Delhi during the winter season, right? The contribution of Punjab decreases in case of black carbon because it's not as long-lived as CO is. So the lifetime of the pollutant in the atmosphere matters. And then now pay attention to this panel here, which is for the summer monsoon season, right? We know that one branch of summer monsoon season goes through the Indo-Gangetic plain. And so you can see that the importance of Uttar Pradesh in Delhi's air quality rises during the summer monsoon season. So the sources that control air quality in a particular location also depend a lot on the weather parameters and phenomena like Indian summer monsoon. So I call this as a Delhi airshed. So if Delhi has to solve the air quality problem, we need to work together this with all these states. It's an airshed problem. It's not just Delhi's problem. And that's not only true for Delhi, it's true for every state in India. So direct emissions are affecting, the transport from the other states are affecting, and then this led to these type of events, right? 8 November 2017. This was really the start of our journey of this evolving story of science in service of society. 8 November 2017, it is called a red letter day. The air quality index reached 999. Indian Medical Association declared a public health emergency and cold conditions equivalent to smoking 50 cigarettes a day. So even if you are a non-smoker, you are inhaling that much smoke. Kejriwal called it a gas chamber. So now you can relate how politicians react when smoke episodes happen. The LA mayor said we can solve it in 4 months, and we haven't solved it in 75 years. There are health estimates that shows a person on average loses 6.5 years of their life because of exposure to air pollution in Delhi. But now the question is, after 70 years of investment into fundamental atmospheric science, building these models, we are able to make predictions. Were we able to provide an early warning to the Delhi residents that this episode is coming? So the WRF-Chem, which is a highly used model, it's called weather research and forecasting model coupled with chemistry. It was operationally running at the time when this episode happened. And sorry, let me skip over this part. This is what we get. This is what they get. So in black here, so this is a daily average time series of PM 2.5. In black, we have the observations, and in red, we have the model prediction. And this is the event that I'm talking about, 8 November 2017. So if you give this prediction to a decision maker, they will throw it to dustbin because this is of no use to them. It is maybe performing reasonably okay. And by the way, this is here the Diwali episode, right? With the firecrackers. It happened to be in October with better dispersive conditions. So it didn't lead to as much pollution that year. But then this was a real problem. Nobody saw it coming. And there was no warning that could be disseminated to the public. So that led to our collaboration with Indian Institute of Tropical Meteorology. And it was really a race against time to develop a new air quality early warning system at the time. So the episode happened in November 2017. So December 2017, we had first conversation between NCAR and IITM about like what we can do to solve this problem. We need to at least provide better predictions during the pollution episodes. And so we jointly developed a proposal. We sent it to IITM, and it was immediately approved. As you can see, the emergency of the situation was such that we took the next 6 months to develop a system. So basically, when we were running the system initially, we were just using the model to make predictions. As I said, there are so many parameterizations that go into the models. There are errors in the input data sets that go into the models. That is why the models make errors. And that's why the model was wrong. So basically here our proposal was that we will constrain the model with observations. We will assimilate the satellite aerosol optical depth into the WRF-Chem model every day before we launch a prediction. And so we tested the system. It showed encouraging results to us. And then we implemented the system operationally in October 2018. For the first 3 months, we kept running the system at NCAR, but then we transitioned the system finally to IITM in January 2019. And IITM has the capacity, they had the expertise required to keep the system running operationally. So Dr. Sachin Gude's group is keeping it operational since then. But then the question is, the new system that we designed, did it help at all, right? So it is the same slide that I showed before. And this is the prediction with the new system in blue. So just by constraining the model with the satellite aerosol optical depth observations, we were able to improve the accuracy of PM 2.5 predictions during that episode by 200 micrograms per meter cube. And I can give another talk on just what are the things that we did into the system, but this is just a highlight that I wanted to. So the thing is, when we have the aerosol optical depth, then we have a spatial distribution over the entire northern Indian subcontinent. When we assimilated that, we corrected for the aerosol load over the entire northern Indian subcontinent. And because the wind system was so stable that these improvements did not get lost in the forecast because of the other errors. And so we benefited from better initial conditions. Plus, we also benefited from the transport of pollution from Punjab into Delhi. So it was, even though only one observation was assimilated, but I think we got more benefit from constraining the spatial distribution of pollutants. So that was one factor. Another factor was, we know that these aerosol particles, they interact with radiation. And so we found that nearly 50% of the improvement during this episode was because of better simulation of aerosol radiation interaction. So Diwali episode, I think most of the firecracker emissions, they happen during the night time. And remember, the satellite overpass time is 1:30 p.m. And so we could not capture it anyhow because those emissions happened at a time when the satellite was not seen. So this is based on the first 24 hours of forecast, but we have shown that we still retain 70% accuracy even on the third day, which is the 72-hour forecast. Sorry? Yes. So basically, so today, so the forecast that IMD has made today, so today is 24, so they have extended it to 5-day forecast now. So now you can get forecast up to 29 December today. Okay, but then it's only an information about the pollution, right? You know whether you will have high air pollution or low air pollution. But if you want to make a decision, you need to know where the air pollution is coming from. Right? So we developed, and this was led by Gaurav Govardhan at IITM Pune. It is again based on the tracer approach that Manish sir was talking about that we developed back during my PhD and postdoc days. So we developed a decision support system to forecast what emission sources are contributing the most to air pollution in Delhi. So it is very similar to the approach that we took during that interstate transport study. And I'll play this animation, and then you will see the challenges in air pollution mitigation that arise because of the changes in just wind patterns. So here what I'm showing is I'm showing the percentage contribution of each of the district around Delhi to PM 2.5 in Delhi. So you see here right now the Delhi's contribution is about 20%, right? A lot of stuff is coming from Alwar, Gurgaon, Faridabad, and then I will play the animation and you will see this source contribution jumping around because the wind changes with time. So you see, as we get into night, Delhi gets red, which means it is getting more contribution from its own emissions. As we get during the daytime, boundary layer gets developed, things get well mixed, and then other regions also start contributing to air pollution. Now, this gives a major challenge to the decision maker. If the source attribution is changing so frequently, then how do they make a decision? Should they control sources in Gurgaon? Should they go to Sonipat? Should I go to Rohtak? Should I go to Jhajjar? Right? And so even though you produce information, sometimes producing scientific information does not lead to solution. It might sometimes create more confusion. And so basically then you have to look at an average picture that over a 24-hour period, what emission sources is contributing the most. And that is the information that we provide to the Commission for Air Quality Management. They look at it, they make their own decisions. This is not the only source of information that they use. Yes, the contribution of Delhi emission to Delhi pollution is increasing because during the nighttime, the boundary layer collapses, right? So I'm not sure if you're familiar with the boundary layer, but during the daytime, we get sunlight, the surface gets heated, it goes up. What is the conclusion or the yeah, it's a percentage. Yeah, for entire region. Yes. So this is the biomass burning in Punjab, Haryana, Eastern Pakistan as well. Yeah. Okay, so this type of info, you can go to this website. We keep it operational, or IITM keeps it operational every winter, this decision support system, because it is very, very expensive to run computationally. But this information is generated. So we pass this information to the Commission for Air Quality Management, which also looks at other sources of information, like how is the weather parameter? Is there a forecast of rain? What is the information given by measurement stations? And then they make decisions. If there is indication that the air is going to be polluted, they restrict activities, right? And you might have seen a lot of those examples in the media recently. But all these decisions are informed by the IITM IMD forecasts, where we collaborate with. And when there is a cleaner air prediction, then it goes to normal operation. And so we found that that with these systems, the restrictions that the commission puts in place, we have been able to cut the peak pollution by 18 to 22%. And that is, again, just based on model sensitivity simulation. So I'm not claiming that that number is correct. That is something that we have to verify over time, doing some control experiments. But it showed some promise that this type of information can be useful. So until November 12th of this year, we were really, really happy with this system. We were really proud that we have developed a system that is helping the decision makers in India. But science continues to surprise you, right? Atmosphere is a dynamic system, and you might think you have understood everything, you have designed a system that works very well, and then you fail. This is an iterative process that we all, as scientists, go through. In this slide, what I'm showing you is the near real time evaluation of our forecasts that also go on the website over the last 2 months. So it goes from October 26 to December 22. That's when I grabbed this from the website. And you can see here, I don't know, sorry. You can see here, the observation is in red and model prediction is in blue. So for most of the time, the blue and red lines are overlapping. But when we had the worst air pollution episode here, from 12 to 18 November, we completely failed. This happened for the first time in 5 years. We never had this type of episode where we were not even able to predict the tendencies correctly, leave alone the magnitude. So you can see here, and this is a problem that every forecasting system in the world faced. All the systems were showing an improvement in air quality, and air quality continues to degrade and degrade and degrade and degrade. And one leading newspaper of India called our system as a faulty early warning system, because so it doesn't matter that you perform well for 80% of the time over last 5 years, you make one mistake and you are on the radar. So this is again something that you have to deal with continuously when you get into applied science. And even after that episode, means you can see that we have been tracking very well the air quality. So that surprised us. Means like I was really, really surprised. Like, why is this happening? Because I was really confident that we had developed a good system. So not everything is in your control. So this map here shows the fire locations based on the satellite data. And so you see here a shift in the fire burning practices. So the satellite overpass time is here, 1 to 2 p.m., right? And we take these measurements to estimate how much crops are burning and what is the emissions coming from that crop. And so if you look at like 2019, 2020, 21, the information that you get at this time is mostly representative of what is happening at other times. And because you only have one satellite overpass, you can assume that this activity is going to stay like this, right? And so that assumption worked very, very well over the last 5 years. What happened this year, and this is very preliminary, so do not cite it if you are interested in citing. So now you see that the fire activity at 1 to 2 p.m. significantly reduced. And farmers started burning from 4 to 5 p.m. And so some reporters are saying that there has been a consistent messaging to the farmers that if you want to burn the crop residue, burn it during the evening period. Right? So what happens is, one is you are satellite is not able to see this information. All the forecasting system in the world uses the information from those satellites that come from 1 to 2 p.m. It is evening hours, boundary layer has collapsed. So you are emitting into a much smaller volume. And then this effect, because of the aerosol radiation interactions, doubles. So there is a lot of accumulation of smoke, which then led to fog. So one thing was, you are not able to get the fire activity right into your model. You can't do anything about it. And the second is, the smoke plumes were so thick. These are the MODIS aerosol optical depth maps that we assimilate into our models. And so Indranil sir, this is what I was talking about. Like, if you have observations over this Punjab region, you assimilate those. And so when that flows downwind, you continue to benefit from that. But now, because of the thick smoke and then the subsequent development of fog, satellite was not able to see through. So it was kind of a feedback effect that kind of established itself. And so we neither have better information about the fires, we nor had aerosol optical depth data to assimilate. And that's why, and there were strong winds at the time. And so the model, by the nature of the laws of physics, if there is more dispersion, there is more dilution. So they were predicting an improvement, but in reality, we had a large degradation of air quality. So now the question is, how do we solve this problem? It's a, sorry? So because it has been so fresh that we have not been able to test everything, right? But we are assuming that if we get better information about the fire activity, if we get a better satellite retrieval that actually provides me the values over these missing regions here, then I am confident that our model will be able to predict the episode. This is something that we are working on right now. Around 4 start and around 9, just around 10, 11. But so yes, but and there is another thing, Tarunji. If you look here, means okay, so Haldwani or MP activity is also going to cause problems. It does not get noticed because they are downwind of Delhi. Their smoke doesn't make it to Delhi. Punjab activity is under so much scanner because its smoke directly goes to Delhi. So it's not a issue of like not burning in the evening. People have been burning in the evening. They are just not getting noticed. That is the only thing. So anything that affects Delhi gets very high attention. And if you look at the air quality maps, actually air quality in Haldwani is no better than Delhi. So it is actually same across the, if you look at these maps, like you look at the whole Indo-Gangetic plain, this whole plain is suffering. Only Delhi gets highlighted because it is being measured. It is the capital and it has the attention of the world. Yeah. So it doesn't matter whether you live in Delhi, if you live in Bihar or in UP or Uttarakhand, at least the plains part, air quality is poor everywhere. You may be, yeah. Yes. Yeah. So definitely, I think we have been doing, because MODIS is ending next year. MODIS is dying next year. So we have done some experiments with OCM3 AOD, and we see similar improvement. So we are definitely going to incorporate those. So GEMS only comes over India in the evening time, right? It does not provide us the full diurnal cycle, and it doesn't have a good AOD product yet. Yeah. I think it comes only for 1 or 2 hours. So it is similar to the polar orbiting satellite. All right. So what we are doing to address this? So we have developed this approach. We call it analog ensemble. We know that we cannot predict observations in the future, but we know that atmosphere is a repetitive system, like the weather conditions and the air pollution conditions that occur today. Similar conditions might have happened during the past, right? So if we make a forecast today, and if we have a long enough forecast archive, which we have a 5-year forecast archive um, in case of Delhi air quality forecasting, then I can go back in the past and I can search for analogous conditions for tomorrow's weather and air quality conditions, or whatever my forecast cycle is, right? And you can, as if you are using the same model for your predictions, you would assume that the model would have made the same errors in those conditions in the past as well. So it's a multivariate metric that we calculate, which depends on temperature, pressure, relative humidity, winds, pollution levels, etc. And we compare it with the past forecast. And then what we do is we select observations corresponding to those forecasts. So you use the forecast to find similar situations in the past, but then you collect all the observations corresponding to those forecasts. And then you make an ensemble based on that. And so we did this for Delhi, and we see, like, because in the past we have observations. So if we know similar conditions in the past, maybe it can help. And so this is what we are getting now. This is from 13 November 2024. So this is one of the exercises that was a high priority for us to implement for the next season. And here in open dots, you have the observations, the observed PM 2.5 in Delhi. In black is our prediction. So as you saw in that plot, it's completely wrong. And in red, we have the analog ensemble prediction. So these are very, very preliminary results, but this is really encouraging for us, and we are going to implement it in the next season to see if we can capture these type of episodes better in the future. This is a average of 30 stations across Delhi. But this is only at one station. So here means in the legend you say station 4, I have to check which station it was. But here it is only one station, but we have like 48 stations in Delhi NCR region. Okay. And so it's not over yet. Means you develop a system and then you discover new challenges. So you think you have solved one problem, but that leads to another problem that we'd never thought about. So this happened in 2021. So there was a pollution event. We predicted it correctly. There was some other supplemental information also corroborating that air pollution episode is coming. And so the Commission for Air Quality Management, they put a ban on construction activity. And we never think about the daily wage workers, right, who work in construction industry. So 3 years later, they moved to the Supreme Court of India asking for lifting the ban on construction activity, because for them, if they do not work, they do not have money to put food on the table, right? So it's an ethical question. Sometimes the science that you do can lead to issues that you never think about, right? And so it leads to environmental justice, equity type of challenges. That portion of the society is probably the one that is not causing enough emissions to contribute to this problem, but they are hit the hardest by the policies that we make. And so basically we need to take this thing up. We need to collaborate with behavioral scientists, social scientists into understanding how do we equitably design policies around this issue. And then there are several scientific challenges around this issue. MODIS is ending next year, so what next? We benefit significantly from the AOD assimilation. There is another satellite called VEERS. We have done some experiments that show improvement in air quality similar to what we see in case of MODIS. Now, the decision makers are also pressed very hard because of the effect on these portions of the society, right? So the Supreme Court is now asking them that you need to tell us 3 days in advance what restrictions you are going to impose. And atmosphere is a chaotic system, right? So naturally, even if you have the best initial condition, the accuracy of the forecast will go down with time, right? So the more closer you are to the initialization time, the more accurate the forecast will be. But they say the CAQM says we don't worry about the first day forecast. Give us more accurate third day forecast because they need to tell the Supreme Court. So it's kind of challenging the scientific knowledge, the paradigm. How do we address this problem? Dynamic changes in emissions, right? We just saw the example from Punjab, and then there are marriages happening. So when we failed on 12th November, my first doubt was there are 50,000 marriages on 12th November. This is the first day of marriage opening in Delhi. Every marriage celebrates with firecrackers. How do you account for those emission sources? So that is another challenge that affects the accuracy of our system. So hopefully, maybe we can come up with a rapid refresh system, like we assimilate observations every hour. But if we try to do that, there is a 3-hour lag between when the observation is made and when it is available on the website. So in 3 hours, you make a 72-hour forecast. You cannot wait that long. So there are practical challenges in how you integrate your observations and model. There are large uncertainties in the crop residue burning emissions, as I showed. And then now, with the smart city mission, every city wants to have this system, right? You cannot run high resolution system for every city. We do not have that much computational power. So we have to be very smart. We have to be very innovative in how do we replicate this system for 100 cities. So these are some of the opportunities, some of the challenges that emerged out of this 5 years of investment into this research. And so that's why Delhi air pollution is an evolving story of science in service of society. I know that I'm almost out of time. I have some more topics. I probably don't want to go into that. So maybe we can wrap up here and take questions.
Interesting talk. Now if someone has any question, then.
Sorry. The point is, first of all, it's a very good talk. The point is that what you are doing is solving differential equations, right? So the better initial condition you have, the more processes you include, you will be better, right? But this is, I mean, it's like, you heard of the story of Sisyphus, right? It's a Greek mythology. So it's like this one guy is trying to take one big stone up the hill, right? Every time he goes up, it falls down. Again, it goes. So it's something like this bandar on that, oily pole or something. So the reason, I mean, I remember that this Harshvardhan came here and he was giving like the way you said that they was demanding a lot of things from the atmospheric scientists. And I gave him this terse reply that you will not, it's a losing battle. You will never see all the things that are coming, right? And what's the point in, predicting all these things? You go to Haldwani, all the trees which are 100 years old have been cut down.
Yeah.
They're building, 4-lane, want to build 4-lane, roads on, in the Sivalik ranges. So it's never going to work. There will be landslides. And these idiots don't understand that. Okay, they have one model of development. That means that you will have always, good big roads and etc. Delhi, I have never seen Delhi without some construction going on somewhere. Most of the time I think these are unnecessary. What is the point in, having 40 roads onto the IGI airport? I don't need that.
Well, I do not disagree with that, right? I completely agree with that. I think as we develop, as the mankind developed, I wouldn't just say India, right? So we developed with a philosophy of pollute now and worry later, right? So we have been reactive all this time rather than being proactive. There are agencies that do environmental impact assessment, and those environmental impact assessments are done based on very simplified models. And there are other factors that I won't mention, and you know how the environmental impact assessment process goes, how the clearances are approved, right? So there is a need for us to sit down, reassess our development philosophy and the impacts that are going to have on the society. I think I am seeing that at multiple places, right? Means there was another component of my talk that I couldn't cover. Recently, WHO released the revised air quality guidelines, and they are saying that annual average PM 2.5 should not exceed 5 micrograms per meter cube anywhere in the world, right? And so we did an experiment, and let me actually quickly show you a graph. So here, so we did an experiment, right? We said, let us remove all the humans from the planet, right? Nobody is living on the planet. And we go back to the climate of 1850. So if you have the 10 microgram per meter cube guideline, which was there earlier, then in red here, you see the areas that exceed that limit naturally without any humans on the planet. If you reduce it to 5 micrograms per meter cube, you get this. So basically, this limit of 5 microgram per meter cube is not physically attainable. There are natural sources in the atmosphere that will at least produce that much of PM 2.5. So look at the global agencies. They are making policies looking only at one angle. And we are doing the same thing in development, right? That, okay, we want prosperity we want luxury in people's life, but we are not thinking about anything. And this is happening everywhere. I think as a species on this planet, we need to revisit our thought process in how we are developing. Until then, we will just be doing our business as usual. We will just be making these type of things, right? It is kind of a wastage of resources, our wastage of our intellect. So maybe I will stop here, but I completely agree with you.
So as IC sir rightly mentioned that, it's differential equations that we are solving, Navier-Stokes equation and all those things. But then another component which goes in is like the emissions or the sinks, a part and parcel of it. And as you mentioned, you cannot, even if you have the best forecasting system in place, you won't know if suddenly in Delhi you have, instead of 100 marriages or 1,000 marriages. Okay. But at least there can, but still, are we working somewhere on some sort of near real time emissions inventories? Because without them, it would be very difficult to have the kind of predictions that early warning systems require, one. And second, what are the challenges that you see in building this system, or even in assimilating the upcoming geostationary satellite data into the models? These are very two different questions.
So I will answer the first question first. I think everybody in India realizes the need to have good emission inventories. So I was at Commission for Air Quality Management yesterday morning before I came to Nainital, and we had a long discussion with the chairman of the commission, and he completely agreed we need this. Now, the challenge there is the typical bottom-up emission inventory development process it takes time. So there is a lag of 2 to 3 years in building that emission inventory. So what we need to come up with is we need to come up with a surveillance system that can help us rapidly update those emissions, right? I don't care if it takes developing partnerships between atmospheric scientists and pundits who do marriages, right? Talking to the marriage halls, talking to band wala, baje wala, how many marriages are happening and getting an estimate of that and trying to talk to the people who sell firecrackers, like how much sale has happened, you can at least come up with some estimate. But we need to get out of our disciplines. We need to get out of our silos. I think it is a convergent science problem and it needs a convergent science solution. So that is the first part. On the challenges that we faced in building the system was bureaucratic challenges, right? There are a group of people who did not want us to work on this, right? Emails were sent to my leadership in NCAR saying that we should be stopped. What we are doing is unethical because we are trying to take over somebody else's system, right? People tried to shut down these projects saying that this is just a waste of time, nothing good is going to come out of it, right? Then resources is another issue. We can put, I worked like 16 to 18 hours a day when we developed the first version of the system, but then who is going to take it over? Who is going to carry it over? So I think kudos to Sachin's group in IITM for keeping it operational for so many years, right? You have PhD students who do their PhDs and then they go away. How do you make sure that you retain that capability within the institution? So challenges will always be there, right? We always, if there is a will, wherever there is a will, there is a way. I just believe in that. So I see challenges as opportunities. It helps us think an innovative way to address something. I know that we are providing a very small contribution to a very large problem where not everything is in our hand, but at least I strive to create information that is somewhat useful to somebody. I do not know if I answered your question, but that is my experience.
Thank you, Rajesh, for a very nice talk. So since now this problem is globally understood that, pollution is increasing and a lot of discussion agencies are working on that, forecasting and many other issues, right? And even some of the people came up with some solutions like, putting smoke towers in Delhi or maybe in another places globally. So for example, if we think of weather modification things, like China and other, countries, USA, sometime even in India, this artificial cloud seeding is also going on. But then, this is one way that we put one chemical into the atmosphere in the form of cesium, they will create another, pollution on the surface of the earth. So do we have, global agencies which are focusing on these pollution issues, such a, sort of perspective that people should work towards the technical things or technology developments which are basically clean, since we can't stop development and all those things is part of policymakers, then bureaucracy, many things coming into picture, particularly the political system, which is not in beyond our control in general. So I mean, do we have such thought process going on that let us try to develop such technologies which can mitigate these problems, at a larger scale, not like putting crores of rupees on the smoke towers, but resulting in none. So those sort of things, I mean, do we have such plans in whether in car, WHO, or such discussions basically, which can, some funding can be, invested on that or allotted to that problem, solving problem basically.
So I think a great question, but like Aries, we are also a research institution. Most of our efforts go into better understanding the atmosphere and how we can make predictions more accurate in service of the society. We also work on cloud seeding and NCAR. We have a weather modification group, but I do not think cloud seeding is the solution to Delhi's problem. So for two reasons. One is typically this is a dry season. You have very little cloud. You can only see the cloud if there is a cloud, right? And then the second is, even if you have a precipitation episode, right? If there is a rain for 24 hours, our emissions are so strong, within 18 hours, you get back to that level, right? So I think emission mitigation is the solution. Now, how are we going to mitigate the emission? So first of all, I think the investment into cleaner energy, the renewable energy infrastructure is very, very important. Getting electric vehicles, of course, then there is another issue of the battery discarding, and then so that is there are so many other issues. Like if you are getting your electricity from coal-based power plant, you are just shifting the source from road to the power plant. Yes, so battery disposal and recycling, that becomes a challenge. So again, I think it goes back to Indranil's point that that we only think from one angle. There is no holistic approach, and we are in a rush actually, right? And I do not know if it is common sense, but like it is hard to convince people that we should worry about clean air and not about the luxury in your life. People will never buy that argument. Yeah.
Actually a very good. There is many people around the world. It's not a full answer to you. Partially. It was completely shut down.
Well, actually, it did not make any impact.
It didn't have any impact. Yeah, right.
Yeah, reduce the number of vehicle, that is fine, but odd even is not a solution. Yeah. Oh, yeah. I think maybe last very quick,
Just query.
very quick.
Yeah, Rajesh, that Delhi forecast model, they are using CPCB data, the
Yes.
input.
Yes.
But
So they are-
CPCB data is, they have lot of uncertainty in that.
Well, so when we do the near real-time evaluation, we do a lot of cleanup of that data. Means we reject all the observations that are less than 10 micrograms per meter cube and anything above 1500 microgram per meter cube, which I'm questioning myself now, because the way things are going, in some cases, it may actually go above 1500 micrograms per meter cube. We try to eliminate the impact of sudden changes in emissions, because again, when we are doing model verification, we have to be honest with the model as well, right? If there is a source that is not in the model. So say, for example, if PM 2.5 changes by 200 microgram per meter cube in 1 hour and then comes back, we think it is a sudden emission source that we were not capturing. So we remove those type of data from the events, and then we use them for the verification of our model. Yeah, of course, means like state agencies, they are, yeah. Data accuracy has been a long-term problem in India. Unfortunately, it still continues to be. We are not going to get away with this problem by doing this. If we are not honest with ourselves, we are not going to make any progress.
Let us conclude here. We have very good discussion and also good informative talk, particularly on Delhi issue. Of course, there are a lot of questions. And so once again, thank you, Rajesh. And in the news, there is some small souvenir. Maybe request Indranil to Rajesh. Some memory from Aries.
Thank you.
He was the batch when I joined Aries. He was the batch.
I also just a few months before.
Yeah, you joined a few months before. No, our year.
I joined in April 2006. You joined in end of
2007.
Yeah,
He was in the basically.
He was second year.
I was second year
Second
PhD
year.
student.
Okay. Good talk, by the way.
Thank you.
And we had some round of discussion with the atmospheric student. Still somebody wants to have some more discussion, or anybody is here. Of course, he is in my office, so free to talk to him. Tomorrow also he is here. If you would like me hear me, suppose you have to go with him to Devasthal. He's planning to go Devasthal. Okay.
Yeah, thank you so much, everyone.